We have seen how a radio wave travels from a transmitter to a receiver as the electric field component of electromagnetic energy.
And we have also seen that while transmitting, we have to use higher band of frequency, and we should not use, or we cannot use, lower band of frequency because of the limitations of antenna size, because of the limitations of radiation power, because of the limitations of number of channels that can be provided. Due to all such limitations, we will decide to use higher band of frequencies. In higher band of frequency, we will prefer using HF band, VHF band and UHF band. Out of these bands, HF band, in HF band of frequency, as we have already seen, the transmission of radio waves is due to, or mostly due to, refractions at ionized layer of atmosphere. Or in all other band of frequency, normally the transmission is due to line of sight or space wave transmission. Now in this, initially what they have done, initially they have started with just sending higher band of frequency by switching it on or off for certain duration, and depending upon the duration of switch on and switch off, they used to decide what exactly the code or information is there in the carrier or in the radio frequency. This type of transmission where you are transmitting higher frequency by just switching it on for some duration and switching it off for some duration is mostly utilized in Morse code transmission. As we shall see, in Morse code, it is just simply switching on and switching off of radio high frequency wave, and there is no specific superimposition of any information.
The simplest form of modulation is to switch the electric current on and off. This is called keying. Morse messages can be sent in this way. Keyed carrier waves are designated A1A, and they are used mostly for long-distance NDBs, as all of the transmitted power is in the carrier wave. If the carrier wave were unmodulated, it would simply be a radio wave at a constant amplitude and frequency. This type of signal is ideal for direction-finding equipment such as the Automatic Direction Finder, ADF. Its waveform would look like this. If the carrier wave were transmitted at a frequency in the audible range, one would hear a continuous tone, like this. Radio signals are designated according to their characteristics. The unmodulated carrier wave is designated N0N. Let's examine these designators given to various types of modulation. Have a look at this table, which explains the three-letter system. The first character defines the type of modulation. The second digit gives the nature of the signal, and the latter the type of information carried. For instance, the first N in N0N shows that the carrier is unmodulated. 0 means that there is no modulating signal, and the second N indicates that no information is transmitted. Now use the table to decode the designations which are listed here. We now need to look at how information, called intelligence, is superimposed onto the radio wave. When this is done, the radio wave is termed a carrier wave, and the intelligence is said to be modulated onto it. More sophisticated intelligence can be superimposed upon a carrier wave by modulating either the amplitude of the carrier wave, AM, or modulating its frequency, FM. You will be familiar with the term AM radio. This means amplitude modulated radio and refers to the medium wave broadcast band 300 to 3000 kHz. If an electromagnetic wave in the radio frequency bands is mixed with a lower frequency wave, such as an audio frequency, the amplitude of the audio wave will modify the amplitude of the radio frequency. It does this by varying the strength of the transmitted radio current according to the pitch and loudness of the speech wave. The process of superimposing one sine wave upon another, such as an audio frequency on a radio frequency, is known as heterodyning. The process combines the two frequencies, leaving the radio frequency unchanged but producing new frequencies at the sum and the difference of the two frequencies. For example, an audio frequency of 3 kHz and a low power of 50 watts is used to amplitude modulate a radio frequency of 2182 kHz, which has a high power of 100 watts. The radio frequency remains unchanged, but the audio frequency is split into two sidebands. One sideband extends upwards from 2182.001 kHz to 2185 kHz, the upper sideband. The other, lower sideband, extends downwards from 2181.99 kHz to 2179 kHz. The spread of frequencies is therefore from 2179 kHz to 2185 kHz, giving a bandwidth of 6 kHz, that is, double the audio frequency used. Where the modulating waveform is constant in amplitude and frequency, as we have just looked at, it is designated N0N, A2A or N0N A8W. The N0N refers to the continuous carrier wave, and the A2A relates to NDB ident transmissions, while the A8W relates to ILS ident transmissions. The human voice, however, varies in both amplitude, that is volume, and frequency, that is pitch, and so the modulating waveform is complex, and its effect on the carrier wave is shown here. Where the voice communication is in the HF band, the signal is designated J3E. If the signal is in the VHF band, it is designated A3E. The extent or depth of the modulation is measured as the ratio of the amplitude of the modulating waveform in volts to the amplitude of the carrier wave before modulation in volts, expressed as a percentage. Here's an example. If we look again at the way the power of the audio wave and the power of the radio wave are distributed when they are mixed, we can see that the 50 watts of audio power is divided equally between the upper and the lower sideband. The power of the radio wave remains at 100 watts. The intelligence relayed on the modulating wave is the same in the upper sideband as it is in the lower sideband. Therefore, there is unwanted duplication. It would be more energy efficient if one of these two sidebands could be deleted so that the energy were completely saved or applied to obtaining a greater range. It is usually the lower sideband that is suppressed. Similarly, the radio wave, having served its purpose to get the audio information into radio frequencies, is now redundant and should be either reduced or suppressed completely. In addition to the power saving, it is desirable to reduce the overall width of the transmission because skywaves are liable to distortion in the ionosphere. The narrower the width, the less the distortion and the better the signal-to-noise ratio. Because of the demand for radio frequencies in the MF and HF bands, there is an international limit upon bandwidth of 9 kHz in AM sound broadcasting. So, using narrowband transmissions increases the number of channels available. When pure frequency modulation, FM techniques, are employed, the amplitude of the carrier wave normally remains constant. This sine wave represents the information which is to be carried, in other words, the information to be modulated. This is achieved by making the frequency of the carrier wave vary in sympathy with the modulating waveform. So, the peak of the modulating waveform is represented by an increased frequency of the carrier wave. The lower peak of the modulating waveform is represented by a lower frequency of the carrier wave. The frequency of the modulating waveform is represented by the rate of change of the carrier wave frequency. So the greater the frequency of the audio signal, the more frequently is the radio frequency pattern repeated. What then are the relative advantages and disadvantages of the techniques of FM and AM? The advantages of FM are: FM transmitters are simpler than AM transmitters. The necessary modulating power is less than AM. FM reception is practically static-free. The disadvantages of FM are: FM receivers are more complex, a much wider bandwidth is required. The next one to look at is phase modulation. There are two cases. The first is where the input is an analog signal, and the second is where the input is digital. You will recall that the sinusoidal form of a radio wave can be represented by the movement of a point round a circle. Thus, the top of the wave is represented by 90 degrees on the circle, and so on. With analog phase modulation, the phase of the signal is modulated, that is, the rate or speed at which the point moves around the circle is changed. In our example, the modulated signal has now reached 180 degrees on the circle, whereas the unmodulated signal would still be at 90 degrees. To achieve this, it is necessary to change the frequency of the signal for a short time. For the modulated signal to reach the 180 degrees phase in the same time as the unmodulated wave reaches 90 degrees, it must go quicker, that is, its frequency increases. Digital phase modulation, also known as phase shift keying, uses binary numbers as the modulating signal, namely 00, 01, 10, 11. These represent a phase shift in the carrier signal. For example, 00 may represent no shift, 01 a 90 degrees shift, 10 may represent a 180 degrees shift, and 11 may represent a 270 degree shift. Among the advantages of phase modulation are superior noise and interference rejection and enhanced immunity to signal fading. It is used in microwave landing systems and GPS. Let's summarize this lesson. We said that information or intelligence has to be superimposed on the carrier wave. This process is called modulation. Firstly, we looked at the emission designators table so that when we mentioned the designator in discussing the type of modulation, it would mean something to us. We then looked at each type of modulation in turn. The first was simple keying. This is simply interrupting the carrier wave. This is used for Morse code. Next, we looked at amplitude modulation. The frequency and amplitude of the information signal is used to amplify the amplitude of the carrier wave. Single sideband is a technique used in AM. It saves on bandwidth. Next was frequency modulation. It greatly reduces interference from static, but it uses a wide bandwidth. Phase modulation can be either analog or digital. Phase modulation offers superior noise and interference rejection and enhanced immunity to signal fading. It is used in microwave landing systems and GPS.